What's inside a data page? How are tuples organized? How can we read or update a tuple? What's inside the tuple? And how does the system decode it and can understand what's in it? All of these questions will be answered in this video. Hello and welcome. My name is Elhelw. Last time we talked about storage. We talked about the different storage types. We discussed volatile and non-volatile storage. We have talked about database management systems and how the storage is managed in those systems. We talked about the storage manager, how it handles the data transfers between memory and disk. We also talked about data files, how some systems have different files or some systems store all their data in a single file. And these files contain pages, and we talked about some of the different ways pages can exist within those files. The link for the last video is going to be in the description, as well as hopefully on the screen here, so that you can watch it before continuing with this one. So today we're going to go a little bit deeper. So here's again a diagram of what we talked about last time. We learned that data is stored in data files. These files can have some pages along with a page directory. Today we're going to go inside a page and try to see what the tuples look like inside the page. Before we get into the tuples, we also have to talk about the page header. Each page has a header in it that has some metadata about the contents of this page. So this metadata may include the size of the page, things like compression or encoding information about the data in this page, the database management system that wrote this page, the free space in this page, things like that. Aside from that metadata, how is the data actually organized? So just a quick reminder, we are talking about tuple-based databases or row-based databases. There are other types like column-based and so on, but these are handled differently, so we're going to be focusing on row-based databases. We're also only focusing on the pages that contain the table data. So some other pages may contain index data or may contain something like the log entries and whatnot. So for now, we're focusing only on the pages that contain data from the tables. All right. With that said, let's see how this data is organized inside the pages, right? So let's consider some naive approach, right? Say that we maintain like the number of tuples in this page as part of the page header. And let's assume for now that all the tuples have the same size, and we always append things to the end. So the end, we can figure out the end by knowing basically like the offset, like where the tuples start after the header, and also the size of the tuples. So given those and the number of tuples that we have, we can multiply the number of tuples by the size and know where the next tuple is going to be. So as an example, now we're starting with an empty page, so we have the number of tuples equals to 0. If we want to add one more tuple, so we're going to add it at offset 0. And now the number of tuples is 1. So the next time we want to add a tuple is going to be at offset 1 multiplied by the tuple size. So next time we add it here and we update the number of tuples equals 2 and so on and so forth. This approach is simple. It works as long as we have tuples of the same size, but there are some challenges. First challenge has to do with deletion. What happens if I want to delete a tuple? For example, in this figure here, if we delete tuple number 1, now we want the information in the header to reflect the number of tuples that we have. So now it says, okay, now we have only one tuple in this page. But this means that the next time I want to insert something, I cannot know where to insert it just by multiplying the number of tuples by the size of the tuple, right? Because now the number of tuples says 1. But if I want to write at that location, that means that I'm going to overwrite tuple number 2 here. So that doesn't work. The other challenge is what happens if the tuples are not of the same size, right? So again, I cannot figure out where to write just by multiplying the number of tuples by the tuple size, because the sizes are now variable. So okay, so this means that this naive approach doesn't work. So we need something a little bit more sophisticated and maintain a little bit more information than just the number of tuples in the page. So the next approach, which is used in a lot of systems, is called the slotted pages approach. So each page, aside from the header, we also have some slots, and we also have the actual data. The slots are all of the same size. You can think of each slot as basically a pointer to where the data actually is, right? So look at this example here. We have a page with three tuples, tuple number one, number two, number three. So the actual data is stored near the end of the page. And then we have these three slots in the beginning that point to the location of each one of these tuples. So if I want a particular tuple and I know the number of the tuple, tuple number two, and so on, then I can just go to the corresponding slot, find the location of that tuple, and then go and read it. This is, as I said, this is a popular way of organizing the tuples inside the pages. It's used in many systems. For example, in Postgres and SQL Server, they use this mechanism to store the tuples inside the page. Now, as you can see in this figure, the tuples are added from the end to the beginning. So from the end of the page, you have tuple number 1, 2, and 3. And then the slots are added from the beginning of the page until somehow they're gonna converge all the way to the middle or towards the middle of the page. This way, I am trying to kind of like, not waste any space as much as possible. So if we want to insert more tuples, it's going to look like this. So let's say I'm going to add tuple number 4. So I'm going to add the tuple and then add, the pointer in that slot number 4. Same thing, add tuple number 5. Exact same scenario. I can also delete tuples. So if I delete, let's say, tuple number 4, so I'm just going to remove it and then, remove the contents of slot number 4. So now I know that that tuple does not exist anymore. Removing the slot just basically means like, putting zeros or like basically just like a null pointer kind of thing. So the slot will still be there, but it doesn't point at anything. Now, if I want to add another tuple after that, so again, I'm going to add it to the end of the slots and, at the first available space. I can also potentially do some kind of like compaction every certain amount of time to try to minimize the amount of wasted space. So in this case, like I have a wasted space where that tuple number 4 used to be. So I can potentially push everything towards the end and, kind of like, consolidate all the unused space in the middle of the page. Okay, one thing I wanted to talk about in the last video, we assumed that somehow we can magically know which page we want to look into and which file we want to look into and so on. How does that actually work? There is something called record ID or row ID or tuple ID, different names, but they all refer to the same thing. This is basically a unique identifier for each tuple in the particular table. And this identifier can tell us where exactly is that tuple located. As I said, this is unique for every tuple, and it represents the physical location of that tuple. It can be some sort of encoding between, the file ID, page ID, and the slot number. It can also be a function that maps that, ID into these three components. So there's different ways to do that. Could also be some kind of like, internal index with the key being the row ID, and then, it gives you all these three components as the values of the index. So either way, there is always a way to map from a record ID into the actual physical components, the file ID, the page ID, and the slot number, where the tuple is actually placed. In many cases, this record ID is not actually stored with each tuple, but some database systems do that, and they actually store it as like, as a hidden column or a hidden field in the table that you can actually query. So given this information, given that we know now that there's something called record ID, how do we use this to actually retrieve a particular tuple? I'm going to use an example that we used in the last video, but now with this information, you see how this actually works. So suppose that these are the data files that we have. Each file has some pages plus the page directory. And now we want to locate a particular record ID. This might be coming from an index or something like that that tells us, hey, you need to fetch this record. So what happens is that the system will split this record ID into the three different components: file ID, page ID, and slot number. First, it's going to take the file ID, go and locate the file that we want to look into. So now we know this is the file that we're looking at. We're not looking at any other file. Now we're going to take the page ID, go look in the page directory inside that file, which will point us at the actual physical location of that page. So we can go and read that page into memory. And now that we have the page, we can take the slot number, go to that particular slot, follow the pointer, and that will take us to where the actual tuple is located. So this is basically what the storage manager will do when the query engine, for example, hands it a tuple ID. It will do all this behind the scenes, and it will return the tuple that the system is looking for. So, okay, we have seen how do we retrieve a tuple, right? But how do we update a tuple? Let's see what happens when we want to insert a new tuple or update an existing tuple, and see how that affects particularly the I/O, or like the reads and writes from disk. So let's say we're trying to insert a new tuple, right? So the first thing that we're going to do is that we're going to read the page directory. Assume that we're just working from a single database file. So we're going to read the page directory in that file, and then figure out which page has free space that we can use to add in this new tuple that we have. Once we figured out this page, we're going to load that page from disk into memory, right? Now we have the page that we want to write into, it's in memory, and now I can find empty space in that page and write the actual tuple in that space. Assuming that we're not going to write this page to disk right away, let's say there's a separate process that does that. So we had to load two pages. We had to load the page directory, and then we had to load the page where we're actually going to update. So that's like two pages being read from disk. Okay, so that's for inserting a new tuple. What happens when we try to update an existing one, right? So let's say we want to update an existing tuple and set some attribute x to the value of 10. So first thing we have to do, read the page directory. So that's an I/O. We need to find the page that contains the tuple that we want to update. So we already know which tuple we want to update. So from the tuple ID, we can get the page number, and we know which page we want. So now we're going to read that page. Once we read that page, we want to check the slot array in the beginning, and then find where the tuple actually exists. Now that we have the tuple, we want to check, okay, does the new data that we have fit within the existing tuple or no? If we're doing something like set x equals 10, so that's like an integer, usually the old value was an integer, so the new value is also an integer, so it should fit in the same space. So in this case, we're just going to overwrite the tuple in place, and we're done. But let's say that x was not an integer. Let's say that was like a string or something, and we're replacing it with a string of a different size. So in this case, it's not going to fit in the same space that we have for the existing tuple. So what we want to do is actually mark that existing tuple as deleted, and then insert a new tuple with the new information. So that insertion is going to go through the same workflow as inserting a new tuple. So again, we had to load a few pages in this case, both in the insert and the update cases. So that leads me into the challenges that exist with the slotted page technique, right? One challenge is a lot of disk I/O is happening. So we've seen that just for the example that we've shown here, we had to do at least two page reads for inserts, and between 2 and 4 for updates. That's a lot of I/O. The second challenge is that this I/O is random I/O. Especially if you want to update multiple tuples. For each tuple, you're going to load the page directory, and then you're going to figure out which page you want to load as well from disk. That's a lot of random I/O. You're loading pages from all over the place. And we know that random I/O in disk is bad. So that's another issue. A third issue that we have with this approach is fragmentation. Remember the layout of the page. If you're going to delete some tuples, there's going to be some empty space. Besides the empty space in the middle of the page itself, you might have, let's say, a certain amount of space in the page, and now you want to add a new tuple, but that tuple doesn't fit in that space, so you're going to go to put it in a new page. So there's going to be some fragmented space all over the place, which is definitely not good to have that wasted space. So that leads us into a different page layout. So the slotted page layout we've talked about, now there is a different way to store the tuples within the pages. It addresses some but not all of the issues that we just talked about. This new layout is called log structured storage. It basically treats each page as if it were a log. So there are entries that you add to the log one after another. You always append to the end of the log. One other name for this is it can also be called log structured merge trees, or LSM trees, if you may have heard of that. We store the operations or the changes that happen on each tuple. And those operations can be looked at as one of two operations, either a set or delete. If you're inserting a new tuple, that's a set. If you're deleting a tuple, that's a delete. If you are updating a tuple, basically that's a set because you're overwriting whatever was there initially. And each of these operations must include the tuple ID that you are trying to change. So let's see how that looks like. Suppose I'm trying to add a new tuple with tuple ID 31 and has, a single attribute val and equals 10. So this is a set operation. We're going to add this entry to the page. The next operation might be inserting a new tuple, tuple number 32, again with some value. Now I'm going to delete an existing tuple, tuple number 30. So I add a delete operation. Now I'm going to update tuple number 31. So I add another set with the same ID, but with the new value of the tuple. In this case, it's 15. So basically, each time I do a set, I need to include all the data. Each time I do a delete, I don't need to include any data because I'm just deleting the tuple. There can be multiple entries for each ID, as you can see here. So I'm doing set number 31. A little bit later, I'm doing another set for 31, which means overwriting the previous one, and so on and so forth. This scheme or this layout is also used in multiple systems, including HBase, Cassandra, and RocksDB, among others. Now, what happens when the page is full, right? So once the page is full, I'm going to write it to disk in the same order as it is. And then, now I have an empty page in memory ready for more entries. So new entries are going to come. I'm going to, add them to the memory. Once that is full, I'm going to transfer this to disk. And now I have, space for more entries, and so on and so forth. Each time the memory page is full, I transfer it to disk. So now I have these pages on disk that are also ordered by time. Basically, like the most recent is last. And I also have some entries in memory that are also from oldest to newest. Now, what is the advantage of this approach compared to the previous one? One of the advantages is that inserts, updates, and deletes are very easy. We don't need to get any information or locate where that tuple used to be. We're just going to add a new entry to the log, right? All the disk access here is sequential. So I'm writing, one entry after another in memory. Once it's done, I write to disk. I write the next page. Once it's done, I write to disk. So every writes on disk are sequential. I'm writing just one page after another after another. I'm not trying to update any existing pages. There is also no fragmentation. I'm using all the space. So there is no empty space in the middle. Again, all the entries are just one after the other. There is wasted space though, because I have multiple entries for the same tuple ID. Instead of just storing that tuple once, I may have lots of different entries each time I change something in that tuple. So there is wasted space, but there is no fragmentation. Okay, how do we read a tuple? We've seen how do we update and make insertions or deletes, but how do we actually read the value of a tuple, right? So if we want to read a tuple with a given ID, basically, if you remember, now all these log entries are sorted from oldest to newest, and there might be some overwrites. So the current state for any tuple is the last entry that has that tuple ID. So if I want to, let's say, locate tuple number 33, so I need to find the last tuple that has that tuple ID, so I can scan the log from the end to the beginning. So the first time I find something with that ID from the end, this is going to be the most recent entry, and this is the contents of the tuple that I want. Now, scanning is inefficient. Like if we want to scan this whole thing, assuming that it may have lots and lots of entries, this is not the most efficient thing, especially that I might also need to scan what's on disk, right? Like if I don't find it in the memory page, I might have to go and fetch some pages from disk and scan those as well. So again, this is not the most efficient thing. So we can get around that by adding an index. So we may have an index, for example, that has all the tuple IDs and it's pointing to the last entry for each of these IDs. So if we look here, number 31 is pointing to the last entry that has 31. Every time we add new entries, we need to update the index to point to the last entry for each page ID. These entries that it's pointing to may be in memory, or they also may be on disk, depending on how recent they have been updated. So like I said, using this log structure layout, it makes writes very efficient. Reads can also be efficient if we're using the index as we just described. But now we still have a problem of wasted space. We talked about how we have wasted space because we have multiple entries for every tuple. So how do we fix this, right? We fix this by doing periodical compaction. Compaction means that I want to go over the existing data and compact it, remove anything that is redundant or anything that is not useful anymore. So if we look at this example, we have 2 pages on disk that have lots of entries. Some of those entries are referring to the same tuples. So again, remember, the latest state for every tuple is the last entry that has that tuple ID. So all I want is really the last entry for ID 31, 33, 34, 35, and 32. So these are the most recent ones. So what I can do is that I can just take these ones, write them into a new page. And this would basically be the current state of the data, right? I don't need the other pages. Just a quick note that even though we're writing a new page, we're not updating the existing page. We're still writing in sequential order. We may mark the old pages as deleted or something, and we can potentially get rid of them later on, but it's not part of the compaction process itself. We can get rid of those as a separate, job, for example, some kind of garbage collection that collects these deleted pages. Another optimization that we can do here, given this particular example, if this new page represents all the data and there's no prior entries, then I can also remove the 2 delete operations there, because all they're telling me is that tuple number 34 and tuple number 35, they don't exist. So if I remove this part, it's still the same information. If I ever look for 34 or 35, it's not going to be found, which means that they don't exist. If there were prior entries that I have still keeping, then we might want to keep those, because otherwise, if it doesn't find them here, it might go and scan previous pages, which then is incorrect. Another thing is that once we do the compaction, now I have only a single tuple for every ID. So I don't need to keep those sorted by timestamp or from oldest to newest anymore. I can actually sort these by ID, which makes looking for a particular ID much easier. Now I can do index, or I can do some kind of binary search or something like that if they are sorted by the ID. So these are some optimizations to make the search faster and also to compact the space. Of course, once I have something that's compacted like this, the system is still going, so it's still adding more entries. So the following pages are going to be sorted by timestamp again until the next time I do compaction. So every time I do it, I can have one page that represents the current, or multiple pages depending on the number of tuples that represent the current state of the system. Those can be sorted by IDs, but everything that happens after that needs to be sorted by timestamp. We have said earlier that this log structure layout, it makes writing cheaper and easier, right? This is true, but once we add compaction in the picture, this doesn't really hold anymore, because compaction adds more load to the system. If this is happening continuously, let's say it may be happening every time we have a certain number of disk pages, or after every half an hour, or after every n operations or something like that. So this is something that's running in the background. Every time I try to do compaction, I'm doing lots of disk I/O. I'm scanning all these old pages, figuring out which is the last entry for each tuple, and then writing those to a new page. So that's a lot of I/O that's happening, a lot of also CPU if I'm doing hashing or something to locate the last entry for every tuple ID. So again, that's a lot of CPU and I/O happening, which puts extra load on the system. So anything that's happening during that, if I'm doing any disk writes during that, it's going to be slower. Also, the files are getting locked while I'm doing this compaction. I'm locking some of the files in order to maintain a consistent state of the data. So these locked files might become a bottleneck for any other updates. So this means that the compaction process can make the system slower in order to reduce the wasted space. So everything is always a trade-off. So as we have seen, there are multiple ways to organize the tuples inside of the pages. There are pros and cons to each. There is nothing like, a silver bullet that's always better than the others. The best one to use depends on your own system, your own use cases. How much reading versus writing does your system have? What is the data size that you're dealing with? So yeah, there are lots of different factors to consider. And that's why multiple database systems allow different page layouts that you can kind of customize based on how are you using the system. Okay, so now that we've seen what tuples look like inside the pages, let's go even deeper and look at the tuple itself. What does the tuple look like? How do we organize the data inside a single tuple, and how does the system understand that information? So at a very low level, a tuple is basically just a sequence of bytes. That's like the basic unit of storage that the system will understand. Each tuple contains a header plus the data. We've seen every unit has some kind of header or metadata, right? So this header has some metadata about the contents of the tuple. And the contents are interpreted by the database management system. It's not something that the operating system understands, for example. This is something that the DBMS will interpret based on the schema information that it has. Schema information will tell it what are the attribute names, what are their types, and all that stuff. So for example, this is a potential schema. We have each tuple containing 4 attributes: ID, birth date, department, and salary with their types. So then the system will know, okay, if I'm looking for the ID, it's the first thing in the tuple, so I can go read it. I know this is an integer, so I know this is how many bytes of data I need. After that is the birth date. Again, this is the timestamp. I know this type. I know how many bytes there is, so I can interpret that basically like I'm casting a sequence of bytes to the particular type that I'm looking for, and so on and so forth with each of the other attributes. Except this is not exactly how it works. Depending on the CPU architecture that we're looking at, there is the concept of a word. A word is the smallest amount of data that the CPU handles at any given point. You've heard of 32-bit CPUs and 64-bit CPUs and so on. This means that the word is 32 bits or 64. So each time the CPU handles data, it needs to handle blocks of this size. So what does that mean for us? Let's say we're working with a 64-bit CPU. So the word here is 64 bits, right? And let's assume that these are the sizes for the different data types and for the different attributes. So integer is 32 bits, timestamp 64, this character 2, each character is 1 byte, so 8 bits. So 2 characters is 16 bits, and then the integer at the end is also 32 bits. So given the tuple that we have, these are the words. Like if we see the 64-bit boundaries, these are the boundaries that we have. So this means that, okay, the first time we want to read ID. ID is 32 bits, but we only read 64 bits at this boundary. So we're going to read those 64 bits and then just ignore the second half and take the first half and interpret that as a 32-bit integer. But what happens if we want to read the birth date? Birth date is 64 bits. It's kind of like spanning 2 words. Like it's on the boundaries between the first word and the second word. Part of it is here, part of it is there. So how does the system read this? Like maybe it needs to read 2 words, but then figure out where does it start in the first word and where does it end in the second word. It's very complicated. So in order to avoid this complication, the systems usually do something called word alignment or padding, which means that it tries to avoid having any data bit or data attribute that spans multiple words. So in this case, the ID, for example, because it's 32 bits, this means that, okay, the other 32 bit, what do I do with them? We look at the next attribute. The next attribute is 64, so it does not fit in there. So, okay, it said I'm going to pad that first word with zeros, and I'm going to start the next attribute at the word boundary. So the next attribute, birth date, is 64, so that pretty much fills the whole word. Department is 2 characters, so that's 16 bits. I can put it at the start of the next word. The next one is an integer, which is 32 bits. That can still fit within the same word with the previous attribute because it doesn't go beyond the word boundaries. And then, and then I have to pad that last word with an empty space as well. So this way, anytime I want to read something, I know that I'm reading a single word. It might be part of that word or it might be the full word. That's fine, but I don't have to read multiple words and then figure out how to, get different pieces and stitch them together. So this means that the actual size on disk that we use for every tuple is actually larger than, or potentially larger than, the sum of the sizes of the individual attributes because of this padding. It's kind of like, slightly wasted space, but it helps simplify the way we read data from disk. This raises the question of, would all data types fit within one word or not? For most data types, that's okay. Integers, big ints, and so on, they usually fit within one word. For larger or variable size attributes, that becomes more of an issue. If something is larger, like a text field or string or varchar and so on, if it's still smaller than a word, sure, we can put it directly as we've put the data within a word, as you have seen. But if it exceeds that size, so basically padding is not going to help, because if it's bigger than a word, then even if we do padding, we're going to have to put it in more than one word, which we want to avoid. So in this case, we're just going to put a pointer in that place and then put the actual data in a separate location, like a separate page or something. So we might have all the oversized attribute values in a separate page, and then in the original tuple, we just have a pointer that points at that location. In some particular types that are very, very large, like blob types and so on, we might actually need to put those in a separate file entirely and just put the file ID in the tuple space itself. In that case, those files are not usually managed by the system and can be manipulated externally. All right, so to summarize, again, this is a continuation of the last video in which we were talking about the storage. We talked about what's inside the data pages, how the tuples are organized. We talked about slotted pages, and we talked about log structured pages. And those are two different ways to organize tuples inside the page. We also talked about the contents of a tuple, how the data is organized inside the tuple, how the system can interpret these different attributes. And then we talked about the padding to align each attribute with a word, or to make sure that no attribute spans multiple words. And larger attributes can be stored in separate ways, for example, in separate pages or in separate files entirely. With that, this is the end of the video. Please like and share if you found this to be useful, and subscribe to the channel if you want to see more videos on more topics and to get the updates right away. Thank you so much, and see you in the next video.